So welcome to the Mesmer Research Group guest speaker series. I'm Amanda Banks. I'm a research associate in the Industrial Systems Engineering and Engineering Management Department at UAH. And I am very excited to be hosting Dr. Tylen Topçu from the George Washington University. He is going to be speaking to us today about his towards a socio-technical theory for architecting complex systems. I'm very excited to hear this lecture. And with that, Dr. Topçu, I will let you take it away.
Thank you very much for the introduction and organizing this, Amanda. And it's my pleasure to be among you today and virtually visiting my alma mater. And well, today I will talk to you about my recent work on towards a socio-technical theory for architecting complex systems. The overview of today's talk is like the following. First, I will talk a bit about myself and my research interests. Then we will talk a bit about complexity and decomposition theory. Then we will talk on to discuss these new method that we've been working on at GW, which is called solver-aware system architecting, which is basically a technique for bringing in the solvers and their solving processes into the architectural decision-making process. And finally, we will talk a bit about how we can move forward from this point on to develop the sociotechnical theory for architecting systems. So a little bit more about myself. Well, I was born in Istanbul, hence the accent. And growing up, all I ever wanted to do was to design complex engineer systems. So I enrolled into the Middle East Technical University in Ankara and got a degree in aerospace engineering. And after graduation, I accepted a job offer from Rockets and Missile Industries in Ankara to develop the Hisar missile system, which was the first domestically developed air defense missile system in Turkey. And this was a gigantic innovation challenge for Turkey that costed around like $570 million. And we were tasked to develop this critical technology that is subject to export license restrictions. And I had the opportunity in the industry to learn firsthand the difficulties of making engineering design decisions under uncertainty. And I also realized that we lack an empirically grounded rigorous theory for making these decisions. So I decided to go back to school, and I enrolled into the University of Alabama in Huntsville. Dr. Kalopi was kind enough to offer me an assistantship position, and I did my master's degree with Professor Mesmer. And I learned about how we should be making engineering design decisions under uncertainty. Then I figured out that I need to learn a bit more about social systems that produce these engineered artifacts that we are dealing with. So I enrolled into the Ph.D. program in Industrial and Systems Engineering at Virginia Tech. And I focused on the management systems track, learning more about the socio-technical systems. And finally, since last July, I've been a postdoc scientist in the Engineering Management and Systems Engineering Department at the George Washington University, focusing my research a little bit more on the engineering management side of things. So to summarize, I conduct interdisciplinary research, bringing together systems engineering, microeconomics, and data science and optimization to study measurement issues in complex systems design. And since we are dealing with interdisciplinary and socio-technical phenomena, I developed this expertise in applying mixed methods, multi-level research approaches, and I got two research foci. The first one is management of safety critical systems, such as air traffic and rail control systems, where human decision makers collaborate with autonomous decision-making systems. And the second one is focusing more on the design piece of things, and it's on architecture and decomposition theory. And to be able to provide this, provide the research setting, I often leverage government and industry partners such as MITRE, NASA, Infrabel, the Belgian National Railroad Company, to conduct my research, but also to provide feedback from the reality regarding whether if these theories that we are developing are reasonable or not. So going back to my two overarching research teams, I mentioned that one of them is management of safety critical systems. And in my dissertation, I tried to operationalize Jens Rasmussen's safe operation envelope for socio-technical systems, working closely with Infrabel, the Belgian National Railroad Company, who manages one of the most dense and complex infrastructure systems in the world. And we focused on stuff like how the critical decision makers collaborate with autonomous systems, what influences their decision-making, what are the impact of social factors, and so on. And I continue this line of research for the duration of my postdoc at GW. I'm actually the PI for a MITRE-sponsored FAA project on investigating how we can extract meaning from the safety reports of the airline pilots by integrating qualitative research techniques and machine learning methods. And my second research stream is architecture and decomposition theory. And I actually got involved with this research here at the UAH. And I started off with traditional systems engineering, and I moved on to how we can articulate stakeholder value models such as end users and design organizations, and how we can incorporate these preferences into our decision-making process. And then I continued this line of research by investigating how do systems engineers use the mechanisms of abstraction and elaboration to conduct design activities and coordinate work among collaborating design organizations. And lately, I've been focusing on this NASA-supported research program on how we can develop decomposition theory and solver-aware system architecting that revolves around a set of experiment and analysis about the Astro B free flyer robot. And today we will be mostly talking about this piece of my research. However, I also have different versions of this talk where we can focus on some of the other stuff. So first section of my talk is about understanding complexity. And this research has been supported by my mentee, Mr. Anthony Hennick, who's a Ph.D. candidate at GW, and my postdoc supervisor, Professor Zoe Schoenfarber. So let's move on. Well, complexity is an emergent property of systems that arises from parts interacting in non-simple ways. And we have been dealing with complexity for many decades now. However, we are still struggling to deal with it. And when you look across numerous government accountability office and industry reports, we observe that we are still blaming complexity for the chronic failures of systems engineering, such as scope, schedule, and cost overruns. And this is prevalent across both government and industry programs. So why is this happening? I mean, we need to address that question. Well, if the Greek philosopher Plato was alive today, he would tell us any compound, however it's made, which lacks measure, must necessarily destroy its components and first of all itself. Well, again, if Plato was alive, we will nudge him and tell him that, hey, Plato, we were able to design the F-35. It didn't really destroy itself, but it almost destroyed our budget. Well, this brings up the fact that it is very difficult to manage something you cannot measure. Therefore, measurement is a necessary precursor to be able to manage complexity. And we are not the first researchers that developed an interest in this. There have been numerous attempts trying to measure complexity. However, these greatly diverge in terms of how to do it. So how should we be approaching complexity remains an open-ended question. So our motivation in this avenue was to first benchmark these diverging complexity measures based on the understanding of the literature regarding what complexity entails for engineered systems. And then we wanted to propose a rigorous testing strategy for cross-validation. So what we did was we went out to the literature and I identified a set of representative complexity measures. But to be able to do that, we first needed to survey the literature. And we found out that most of these measures either focus on the physical artifact itself or they focus on the descriptions of the system. And they operationalize the concept either based on the row counts or a combined weights and counts of the elements, or more of a topology, overall architecture-based measures. And to be able to obtain a representative set from this wide spectrum of measures, we decided to pick a measure from each of these buckets. And we tried to pick the original ones that were initially proposed, like the first ones, the pioneers. And when there were numerous measures in one bucket, we tried to pick the ones that are more popular in nowadays use. And even though there was great divergence across these measures, there were three commonly held beliefs that were supported by pretty much all of them. So if we were to represent a system through this design structure matrix, where rows and the columns represent the elements in the system, and the off-diagonal elements represent the interfaces and the interconnections, this is what the literature thinks. Increasing the size of a system or increasing the number of interconnections within it should drive its complexity up, and establishing a modular structure in an engineered system should decrease its complexity. So the literature pretty much thinks about modularity as a way to manage or decrease complexity in this perspective. So what we did was basically what Dr. Farrington would do. I don't know if you guys remember Dr. Farrington. So we articulated a design of experiments approach in such a way that its dimensions match these commonly held beliefs of the literature. So we created 3 levels for number of interfaces and size, each representing low, medium, and high. And we created 2 levels for the structure, representing a random structure and a perfectly modular. And to be able to avoid representation issues, we artificially created system architectures to fit these descriptions. For example, we created this low size, low number of interfaces matrix with a random architecture, or we created this medium size, medium interface architecture with a perfectly modular structure. Then what we did was basically we traversed around this experimental design space, holding all else constant, implemented the complexity measures, and investigated whether if they can detect these controlled stimuli in terms of increasing size, interconnections, or reverting a random architecture into a modular one. And the results were quite interesting. So the rows over here represent the measures that we have implemented, and this column represents their ability to detect changes in size. Well, we were surprised to see that only one of the measures consistently detected increases in size as an increase in complexity, whereas one of them thought it was decreasing complexity and another one was totally insensitive about it. It didn't even see changes in size. And 3 of the measures exhibited an inconsistent response that varied depending on the baseline case of the architecture. When we looked into their ability to see the changes in interfaces, we observed broader support there. And more interestingly, when we looked at their ability to detect changes towards a modular structure, we have seen that half of the measures were completely insensitive towards modularity, meaning that if an architecture had a certain number of elements and interconnections, having a modular structure or a totally randomized structure had no impact whatsoever on the measure. And only one of the measures that we looked into was able to detect these changes. So we wanted to dig a bit deeper to figure out what's really going on. And we observed a dichotomy in the literature regarding how people think about complexity and where their perspectives comes from. So there's this first group of researchers that are approaching the problem from a more engineering design perspective. And when they think about a complex system, they are thinking about a physics-based system that has tightly interconnected parts, often with high degrees of modularization, such as a space-time system, a satellite, a tank, etc. And there's a second group of researchers who are thinking more of a flow-based system when they are thinking about a complex system. And these researchers usually originate from computer science, network science, or graph theory, etc. And when their understanding of complexity is more of a sparse structure with less regulated dependencies. So to test this observation, what we did was we pulled out 2 typical architectures, one of them representative of the physics space and the other one representative of the flow base. And we asked these 6 measures, which one of them do you think is more complex? And we observed that measures coming from a flow-based understanding predominantly thought the flow-based system was more complex, whereas the other measures coming from the physical side of things, they thought the physics-based system was more complex. So where does this leave us? Well, in an increasingly interconnected and cyber-physical world, this dichotomy is extremely concerning because we are seeing more and more of systems that are a mix of both kinds. And the implications for our community is that we need convergence, not divergence. We need communication and we need openness in terms of sharing our representations and how we approach these problems with each other. And we also need more cross-validation work because, I mean, when we design engineer systems, we don't feel them without validating them. Therefore, we need to be careful about when we are proposing these measures, which we claim to be generalizing across all the cases of complex systems. Okay, moving on. The second part of this talk is about understanding decomposition. And for this piece of research, another PhD candidate from GW, Suparna Mukherjee, who's a seasoned NASA roboticist, joined us. And what is decomposition? Well, decomposition is a dominant strategy for managing complexity because it enables problems to be broken up into more manageable chunks or modules. And it has many benefits. For example, it has schedule benefits because it allows us to divide and conquer the problem, and it enables parallel processing that reduces the overall design iterations and time. It has many organizational benefits, such as reducing the need for the multidisciplinary knowledge that is required to solve a design problem. And it allows us to better facilitate domain experts, such as an electrical circuit designer or a mechanism designer, etc. And it also has innovation benefits because modularity can enable organizations to focus their creative energy and create mass customization opportunities that could allow them to expand their customer base. And also there are approaches such as multidisciplinary design optimization that allows us to optimize for an ideal solution on a system level. However, modularization is not a one-way street, because like over-modularization has many risks, particularly when key interactions in the system are missing, or there are many system-level conflicting objectives that needs to be coordinated. Okay, well, there's a research gap regarding decomposition in the literature, because when we survey the literature, we see that we are predominantly trying to group elements of a system when we are thinking about decomposition. People are either trying to group functions for changeability and mass customization, or people are trying to group components for streamlining manufacturing efforts. And this can be visualized like this. So I assume that these nodes represent the elements of a system and the arrows represent the interconnections between them. We can convert this representation into a design structure matrix. And what the literature is pretty much trying to do is to reorder and cluster the elements of this matrix in such a way that within module dependencies are maximized and out of module dependencies are minimized. However, this is a rather peripheral perspective given the complex interdependent nature of systems. I mean, you cannot really reorder the elements of a complex engineered system like you're shuffling your Spotify playlist. Why? Because they're interdependent on each other. And this approach often overlooks the traditional purpose of system architecting, because we need to manage this conflicting system level objectives. Therefore, we need to be mindful of how we can arrange these elements or not. Also, when we look into the literature, we see that most of these reordering clustering based approaches either verify on a certain kind of system or they focus on abstract representations such as the design structure matrices that I just showed you. And there's some evidence indicating that these methods do not necessarily scale well to complex engineered systems. Well, if we recall Herb Simon the Great, we know that complex systems are only partially decomposable. And we think, as GW researchers, modularizing physics-based systems inherently introduces additional information and complexity into the problem space. And we wanted to document this through a detailed case study of a NASA robotic manipulator to be deployed on the International Space Station. So going back to my mixed methods research approach, we adopted a case study where NASA engineers were developing a robotic arm manipulator that is supposed to be mounted on a robotic free flyer. And it was expected to connect the free flyer by attaching to the outer handrail of the International Space Station. And it was expected to tilt and rotate in certain directions to allow the free flyer to take images and so on. And alongside these AstroBee experiments, what the NASA engineers were trying to do was they were creating a decomposition of the same exact system, this time decomposing this robotic arm from shoulder to elbow and from elbow to down. So they created two modules. The first one is a positioning mechanism, which is shoulder to wrist. I'm sorry, I said elbow, is shoulder to wrist. And the second module is basically the robotic hand. And they allocated the functions in so that positioning mechanism was supposed to plan, deploy, stow, pan, and tilt. And the attachment mechanism was supposed to plan and attach to the handrail. And what we are doing is we are basically comparing the problem specifications for D1 and D2, the undecomposed problem and the two module decomposition. And we are doing it as the following. We are first taking the functional descriptions of both problems, and we are coding this design information in such a way that we can capture the dependencies between these problem specifications. And then we are translating this information into a design structure matrix notation while following the design process in parallel. And converting them into the design structure matrix, even though it hides a lot of information, it also allows us to represent a lot of information in a concentrated way. For example, these two DSMs represent D1 and D2, D1 on the left, and you can visually see how the elements within this system problem descriptions grew. For example, the red area over here represents global system definitions. For example, what being attached to a handrail means in useful engineering design terms. For example, in this case, this involves including a concept for a fixed attachment that is defined as being able to resist slipping or twisting when subject to a specific moment load. The blue lines represent the functional descriptions, and these describe what the artifact needs to be able to accomplish. The yellow area, which didn't necessarily exist in D1, represents the internal interfaces, which implicitly needs to be defined as soon as we make the decision towards having a decomposition of the system. And finally, external definitions like the operational environment are represented in green, and this didn't really change. And when we look at the simple count of these elements, we can observe how the information grew. However, of course, we didn't stay there. Going back to our talk about complexity and its measurement, while now that we have the DSMs, we can actually quantify their complexities. So this black horizontal line on the 0% line on the y-axis represents the complexity score of the D1, and the blue bar plot represents the complexity of the two-module decomposition. And we basically conducted a bounding analysis, establishing a lower and upper bound. This is a form of a sensitivity analysis, trying to understand relatively how complex the two-module decomposition is. And we were surprised to see that in the worst-case scenario, it is 325% more complex, and in the worst-case scenario, it is 75% more complex. This is supporting our insights regarding decomposition, could also be introducing a lot of information to the problem space. However, we were more surprised to see that individual modules, such as M1 in this case, was also more complex than the D1 baseline, and the D2 decomposition were pretty much in between, depending on how you quantified complexity. Well, we wanted to find out why and how this is happening, so we followed the qualitative path here, following the design process, and we identified three mechanisms. The first one is interface creation. And by the way, all of these three mechanisms are quite intuitive for seasoned designers. However, the catch is that none of these mechanisms are represented in the decomposition literature, and therefore they are important. The first one is interface creation. Well, as soon as you make a decision to decompose a system, information needs to be introduced to the problem space to define this energy, material, and information flow between the modules. The second mechanism is functional allocation. Functions on the system level functions either need to be allocated directly across the two modules, or they need to be decomposed and allocated among the elements. And it doesn't really stop there, because there are secondary effects that flow down from this functional allocation decision. Additional decisions need to be made to enable cohesion and coordination among these two modules to be able to function together as a team. And also, additional information needs to be defined to be able to manage the interactions of this overall system with the environment, because this, for example, we need to make sure that this robotic arm, when working in two modules, is not going to damage the International Space Station's rail or the robot or the astronauts around them, etc. So to conclude, decoupling partially decomposable modules can require significant additional design work with associated consequences that introduce considerable amounts of information to the design space that could be unevenly distributed, such as the case that we demonstrated here. And for the first time in the literature, we documented how these decomposition processes can induce complexity growth in three mechanisms. By the way, we would like to clarify that we are not arguing against decomposition here. Decomposition still has many benefits. However, we need to be mindful about the information generating side of it, and we cannot necessarily think of decomposition as a complexity reducing act. And we think that these three mechanisms should generalize to any complex system because they stem from generic interactions. And we only investigated a basic two-module decomposition here. However, if we were to investigate a more exotic formulation, it could very well be the case that the situation would be worse. So the implications for the systems engineering community is that we cannot continue to assume a fixed representation of the system and pursue pure reordering clustering-based approaches to establish the module boundaries. That's not going to work. All right, let's move on to solver-aware system architecting. And we conducted this work again with my supervisor, Professor Zoe Schoenfarber, and Professor Hila Lifshitz-Assaf from NYU Stern School of Business. Well, I didn't tell you this, but my understanding of systems engineering design is that it's a socio-technical innovation process where we are continuously striving towards achieving the boundary of what is technologically achievable. And the issue with the systems architecture literature today is that most of our research focuses on purely technical objectives, such as grouping system attributes like the stuff that we just talked about, or developing strategies against an uncertain operational environment by building in system lifecycle properties, such as these ilities of commonality, modularity, flexibility, etc., or building in real options into the system so that they can be summoned at a later time by the user if need be. And consequently, innovation or advances in systems engineering has been pretty much constrained to the subsystem level, meaning that we've been making more of incremental advances. However, when we look into the management literature, there's significant evidence that was pioneered by Conway's mirroring hypothesis, documenting the linkage between the technical part of the artifact and the social system, the organization that creates it. Moreover, when we look into modern day industry, we see that non-traditional design organizations, such as gig work contractors or open innovation challenges or inducement price challenges, etc., design competitions are increasingly being leveraged. For example, look at this bar plot that visualizes the number of price competitions and the number of federal agencies that have been seeking price competitions have grown over the years. So long story short, this is a time for us to rethink our architecture approaches with a socio-technical lens so that we can utilize this vast knowledge of the crowd that is available outside the boundaries of our technical design organizations. However, there are many obstacles to this because both the innovation theory and the systems engineering literature predominantly assumes that the kind of problems that we are dealing with are expert-only problems, meaning that, it is rocket science that we are dealing with. So we require purposefully cross-trained experts who have high degree of familiarity with the context and who have perfect command of the domain's tacit knowledge. Because these kind of systems that we are dealing with, they tend to draw on multiple naturally uncorrelated skills. So you must have heard of this talk of this T-shaped personality, where an expert has this deep knowledge about a specific area, and they have the ability to work outside of their core area. And when I'm thinking about the T-shaped personality, I would like to think of Inspector Gadget, who was purposefully trained to be an inspector. However, he's also able to work outside his core area because of his excellent mechanical skills. He can fly, he can pull out the hammer on you, and so on. However, in reality, experts are not as exciting as Inspector Gadget. They look like this more European Space Agency's concurrent design team, which is composed of engineers from different disciplines and interdisciplinary team working together to handle this complex engineering design problem. Well, while these experts are awesome and they get us to the promised land more often than not, their accumulated depth of knowledge can also be a double-edged sword, meaning that since they are conditioned in their epistemic cultures, they develop cognitive constraints regarding a problem, which creates this innovation blindness. And this simply originates from the fact that, oh, we have done it this way the last time we were doing it and it worked, or like this is how we do it at this organization kind of a mentality. And well, this prevents them from exploring frame-breaking novel solutions. And also, we have so many cross-trained domain experts in the world. So they are a costly, limited resource to use. Therefore, there's an opportunity if we can bring in this outside knowledge into our organization. And there's evidence that these non-experts have contributed to many stubborn STEM problems. However, they were only able to do so for bits and pieces of these problems, not on the whole problem level. The problem needs to be framed accordingly. Therefore, many in the literature believes that these non-experts can't really handle complex design problems due to the high level of interdependencies that are inherent in them. So what's our big idea? Well, our big idea is that joint consideration of technical decomposition decisions, solver assignment decisions leveraging the open innovation methods, and design of contractual incentive mechanisms can actually enable us to improve our design process outcomes. And to be able to explore ideas further, we have constructed this abstract simulation model. And let me walk you through this. Well, first we instantiated a reference problem in context, because this enables us to have an easier intuition about the opportunities for feasible alternative task structures and solver types. Specifically, we adopted the problem of playing a golf tournament as our reference problem. And although golf may seem like an unusual choice, it meets all the necessary criteria to represent an expert-only problem. Well, first of all, it's a game dominated by experts such as Tiger Woods. However, there are plenty of amateurs and aspirational playoffs abound. Second of all, it's a sequentially dependent game, such as the design process, where the difficulty of every next stroke is defined by the results of the last. Additionally, there's variability in both the kinds of tasks associated with playing golf and the availability of amateurs who are qualified to perform them. For example, driving off the tee requires strength, and in contrast, putting requires a lighter touch and an ability to read the green. So every amateur can put, but few can do so reliably. And based on this reference problem, we created 3 alternative architectures based on this undecomposed problem of single hole of golf. We created two module decompositions, DS and LP, and the 3-module decomposition called DAP. And to support easy reintuition, we calibrated these architectures to align to the game of golf again. So the first element, D, drive, is analogous to driving the ball. So we are basically trying to hit the ball from the tee as far as we can. The second step represents the approach phase of the golf game, and where you are trying to aim the ball to get on the green or as close to the pin as you can. The last stage is called putting, and this is where the goal is to basically sink the ball into the hole. Importantly, these different functions each draw on different skills that might be available outside professional golfers in our traditional design organization. So we continued and generated 3 different solver archetypes. We created professional golfers that represent the limited number of subject matter experts that are employed by the seeking organization. They are great and reliable at all aspects of solving in our case. Then we defined amateur golfers, which represent the crowd, and they have much higher variety of capabilities. However, they are both weaker in terms of range and less reliable. Finally, we defined specialist long drivers, and these represent experts in another domain that share one common function with the kind of problem that we are trying to model. So these are pretty much like amateurs in general. However, they're excellent at one overlapping task on which they are the domain experts in that other domain. And in this case, we chose them to be excellent at driving, taking inspiration from Professional Long Driving Association. Then finally, what we did was, for every alternative problem decomposition and solver type, we created these combinations of problem decomposition and solver assignment, and then we simulated their performance within a Monte Carlo iterator. We kept track of 3 measures of interest in terms of outcome variables. The first one is performance, which we measured by the number of strokes each combination had to take to finish 9 holes of a golf game. We kept track of, cost, which we calculated based on the integration cost, decomposition cost, and the cost to execute the tasks. And we also kept track on how much any combination relied on the experts by looking at the number of strokes taken by the experts and dividing it by the total number of strokes each combination had to take. Before going further and analyzing our results, we wanted to verify and validate our simulated model, because at the end of the day, this is an artificial world we created in our computers. So we wanted to make sure whether if we created an expert-only problem or not. First, we looked at what happens if we assign the same kind of solver across 4 different decompositions. And we observed that solver performances are consistent across alternative decompositions. And if we do not combine the solvers, experts are always better and their performance is consistent. We then looked at, so the horizontal black line over here represents the performance of a domain expert solving the undecomposed problem. And the blue box plus represent performance of amateur tournaments, mutually exclusive amateur tournaments of increasing size, again, trying to solve the undecomposed problem. So we observed that undecomposed problem cannot really be solved by the amateur tournaments in a way that it is better than the professionals. So, and the increasing the tournament size had a diminishing returns to scale. So we concluded that we achieved to create an expert-only problem. So we proceeded to analyze the results. So the y-axis over here represents the cost, and the x-axis here represents the performance. And for both of these dimensions, we prefer less to more because we, again, measure performance based on the number of strokes. Each of the dots on your screen represents the results of a Monte Carlo iteration for a problem decomposition and solver assignment pair. And the different colors represent the architectures of the problems. This red dot in the middle of the quadrant represents our expert-only undecomposed problem benchmark. So can combinations of amateurs provide us with opportunities to improve design process outcomes. Well, if the goal is to improve performance, 32% of the alternatives we explored in our case were able to do so. If the goal is to reduce design costs, 28 of the alternatives we explored that are below this horizontal line were able to do so. However, that being said, most of the alternatives we explored were much better than the expert-only benchmark. So 43% of them did far worse. However, a smart set of combinations of problem decomposition and solver assignment were able to dominate the benchmark in all of the cases that we have explored. So to be able to understand how we can utilize these strategies of bringing in the crowd effectively, we conducted a statistical test in our results sample. And we identified two strategies that lead to these dominated outcomes. The first one is to isolate a subproblem in such a way that it matches an external specialty that is available outside your organizational circle. However, we are going above and beyond by saying that you should leverage experts when they are available. I mean, that's quite intuitive. I mean, everybody knows that. What we are trying to say here is that if you're seeking to bring in these experts, you need to decompose your problem in such a way that it fits the type of problems that they are accustomed to solve in their daily work lives. The second strategy is to apply crowdsourcing to search highly variable solution spaces with low entry barrier. And this is akin to alleviate the innovation blindness of the experts, because when posed with a low entry barrier problem, what an expert will alleviate to do is to seek a satisfying alternative which they have utilized before, which they know to work well. However, this prevents them from exploring the entirety of the design space and explore these frame-breaking novel solutions, which the crowd of amateurs can do, because those frame-breaking novel solutions could be the daily solutions they explore in their regular work life. So to summarize our findings, we parsimoniously provided a concept to improve design process outcomes through synergistic combinations of technical decomposition, solver assignment, and incentive mechanisms. Existing architecture literature completely disregards this opportunity and at best focuses on aligning the internal structure of the organization with the architecture of the system they are trying to design. With smart decomposition and open innovation, we could effectively tap into this outside knowledge for a fraction of the price of experts, with very rapid turnaround rates, with minimum risk because of the fact that we get to pick the best alternative in an ex post fashion after they submit their results. And to wrap up, I mean, we only illustrated two strategies here. However, there are many other social levers to explore, which brings us, where do we go from here? Well, there's a path towards developing a solver-aware system architecting theory. Moving from this point forward, we can extend these ideas to a realistic case through probabilistic modeling. How? We can assume that design is a problem-solving process, which requires an interdisciplinary solver pool of a diverse set of solvers with varying expertise in different domains. And we can assume that us, the designers, the systems engineers, have some knowledge of the distribution of this expertise in the solver pool, along with the characteristics of the problem that we are trying to solve. Well, now that we are faced with the design problem, we can make the following decisions. Number one, we can decide on which decomposition approach is more appropriate for our case, considering the downstream impacts of that decision. And number two, we can design contractual mechanisms, which could be employment contracts, consulting contracts, price-based contests, open innovation challenges, value-based contracts, etc., for each of the sub-problems to engage a certain pool of solvers. This is inherently a mechanism design problem. And once we pose the problem, the solvers, based on their characteristics, backgrounds, and knowledge and skills and motivations, etc., will make strategic decisions to engage in this design process, to pick up the contract or not. And consequently, we will obtain individual solver solutions, which will provide us with a set of overall design outcomes. Well, we can formulate this model, but we need data for alternative design problems, alternative decompositions of it, data about the pool of solvers and their capabilities and skills, and data about various contracts that these solvers can be engaged with. Luckily, in our case, NSF previously funded a study that was conducted in collaboration with NASA that provides us with this information, the AstroB experiment. And if we have this model, we can use this model to make predictions regarding what kind of design solutions would be obtained by a pool. And we can again use this experimental field data and compare the predictions of the model to the field data collected from real solvers and their response to the problems. And we can calibrate and verify our model. And once we do that, this would simply provide us with an experimental sandbox, a test bed, which we can explore with multi-agent reinforced learning techniques to extract novel sociotechnical theory for architecting these complex systems. So that's the path forward. So to summarize, our community, systems engineering community, is extremely inefficient at designing complex systems. Our issues are well documented. We need rigorous systems engineering theory to understand the inherent characteristics of the systems and articulate the much needed architecting strategies, because our systems are only growing more complex by the day. And there is an opportunity for us here to utilize sociotechnical design levers to alleviate our acute shortcomings, because at the end of the day, we cannot solve our problems with the same line of thinking we used when we created them. So on that bright note, I would like to thank our sponsors. This work was supported by the NSF, undergrad, CMMI, whatever. And I would like to open the floor for discussions. And thank you very much for listening to me.
Thank you so much, Dr. Chokchi. That was really wonderful and very, very exciting to hear. We have a couple of questions that have come through. First of all, will you make these slides available to our participants after your
Sure.
lecture is over? Awesome. Thank you very
Absolutely.
much. And I'll make sure that those go out once they're available. Second, we have another question. How can we redefine the expert label to bring in more inspector gadget types?
Well, I think the answer to that question lies in adopting a more diverse and inclusive profile, because more and more, the kind of problems that we are dealing with are becoming more and more interdisciplinary, and having ideas and opinions and heuristics from people with different backgrounds, different expertises, and different heuristics is extremely useful. So I think in terms of our policy making and organizational arrangements, we need to be mindful of the kind of problems that we are trying to solve, and we need to be open in terms of exploring novel ideas, novel perspectives, and welcoming for accepting different backgrounds into our organizations. That's the only way I think we can move forward, because we are suffering significantly from groupthink, right? Groupthink and group biases have a significant impact on the kind of systems that we are designing. And we are more and more seeing this in our daily lives when we look at, for example, bias in AI. AI algorithms are making extremely biased decisions, which is stressful to think about given the catastrophic consequences that they have. So we need a more diverse perspective, and we need more cross-training. And also, this was a long response, but I would like to add one more thing. When we look to the past, and when we look at these great scientists that were revolutionary, when we look at Leonardo da Vinci, when we look at Socrates, when we look at Einstein, when we look at Werner von Braun, these were trained in a wide range of disciplines. It's not like they studied mechanical engineering and did a master's in mechanical degree and did a Ph.D. in mechanical degree, just focusing on a certain bits and pieces of extremely specialized problems. They didn't do that. They were well versed in different branches of science and mathematics and philosophy, etc., which I think made them unique and allowed them to create these revolutionary systems for us. So that allowed our society to move forward. And that's the second piece of the problem that I would point out to on an individual level in terms of how we train people.
Thank you very, very much. Victor, you have a question.
Yes, hi. Well, first of all, thank you very much. This is great. I have a question about, first of all, how would you explain the relationship between increased complexity and all these failures and delays and in engineering systems?
Well, Victor, good to see you. And this is a great question, because I personally think that we have to deal with complexity somehow, right? That's our role, that's our job. We need to be able to do it. And arguably, our inability to deal with complexity could be originating from our cognitive limitations. It could be originating from the way we approach designing these systems, such as, you know, that coming from UAH, we have this significant amount of research documenting that requirement-based approach to systems design is creating these undesirable outcomes. It is inevitable if we approach the problem this way. There are some in the literature who think that the way we develop strategies for verification and validation are faulty, which leads us to these extremely undesirable outcomes. So at the end of the day, I think we need to be mindful about how we are making these design decisions, and we need to be careful about the politics involved with designing complex systems. So there's this recent work of Locatelli that was published in 2018, and he's talking about how these like complex design problems across many industries, such as infrastructure programs, not just the DoD programs, are always ending up in these failures or like cost overruns, blah, blah. I mean, at the end of the day, we end up solving the problems. However, they cost us our firstborn child, pretty much. So how do we alleviate that? Well, we need to be careful about the strategic decision-making that is involved with these organizations and how we design their engagement with the design process. Because if you allow the organizations to get away with a certain kind of system that they can deliver, and you also allow them to ask for an extension 10 years later, saying that, hey, we need $300 million to be able to solve this problem that we created, I don't think it's gonna incentivize them to deal with complexity effectively. Because you're basically providing them with a leadway to make more money out of it. So we need to be mindful about these strategic interactions to be able to deal with complexity on a policy-making level. And on an engineering side of things, we need to articulate this missing systems engineering theory. Because what we are doing as systems engineers mostly is that there are bits and pieces of theory that we use effectively, such as subjective expected utility theory or contract design or mechanism design or Navier-Stokes equations or whatever, you name it. However, we don't really have this theory that unifies our discipline. So in the case of the kind of sociotechnical problems that we are dealing with, it is very difficult for us to determine which way is right and which way is wrong and where we should be headed towards. So that's the technical piece of the problem that needs to be solved. And that's where I'm trying to position my research.
Okay, thank you. I have other questions, but I'll
Sure.
let other people ask questions.
All right.
And we've got a question from Chris next.
Okay, hey. Yeah, so some of the things, especially towards the end of the talk that you were talking about, reminded me of some stuff that I at least spent a lot of time reading with and at least kind of tangentially associated in research with when I was working in cognitive decision theory. Particularly, I'm curious how much you've looked at things in the, I think it's called like cooperative problem solving body of literature that at least seems to have some surface similarities to this. Is this something you've looked at, or is this kind of a distinct approach to these sort of problems?
Well, I don't have much exposure to collective problem solving. The way we are thinking about these problems now is to consider the multi-agent perspective of it. So we are excluding the problem in such a way that us as the design organization, as the systems engineers, we are going to make these decisions and pose these problems. And once these problems are solved, individual agents who are not making decisions collectively will make decisions based on their strategies, objectives, and outcomes. So therefore, rather than looking into collective decision-making side of things, we are looking at how these agents with independent pieces of information and independent backgrounds for which we don't have much knowledge about, will make decisions based on the problems that we are going to pose them.
Yeah,
so
I think I should clarify the cooperative problem solving is multi-agent based. It is a branch of like multi-agent decision theory problem solving type stuff.
Right, but the agents in our case are independent from one another.
A lot of those approaches would be modeling independent, distinct agents.
Okay, I mean, that part of the research is future work for me, so I would be happy to take a look into that, but we didn't initially consider an approach based on that.
Yep, thanks.
Right, awesome. Victor, you had additional questions.
So my other question is on your work when you were evaluating the complexity of the robotic arm, when you calculated the complexity of the two separate modules, is it the complexity of one plus the complexity of the other, or is it basically a DSM with both modules designed separately?
Yeah, the latter. So
Okay.
it's the whole. And when we were looking at the individual modules, we looked at the problem descriptions for the individual modules.
Okay. And my other question is, a lot of these systems are getting delayed before they actually get built. And a lot of those delays are involved with the actual design process. And in the case of aerospace system, that usually is a lot of the testing part of that. And so in that aspect, what reminds me is like the Simon watchmaker analogy, where you have the two watchmakers and one of them basically builds it all together and the other one divides it into modules. And basically, so even though the modules might itself be more complex as a whole, it allows to simplify the design process. So even though the actual design engineering artifact is more complex, the design process itself is less complex. Is that, like, how would you go about, talking about that?
Sure.
Yeah.
Well, Simon's analogy is point on. However, he's talking about a clockmaker that makes clocks in mass and distributes them all around. So like when the clocks are coming back, he's thinking about, if it was modularized, we could do that. However, in the case of space application problems that we are talking about, we are usually trying to create something brand new that's only going to be produced maybe once and fielded. So it is sometimes difficult in our cases to pursue high degrees of modularization when we are designing these systems, because there are a high level of system level dependencies that needs to be managed. And when the prime contractor decides to over modularize a system, we are also working on this on the side. So you give up on your authority to control these system level interactions. So you need to set boundaries early in the design process and contract them out or whatever, define the interface and how they're going to work. And then the individual modules will be designed by someone else. However, if you figure out that you've been missing something halfway through or whatever, it is much more difficult for you to fix those problems later on. So there's a trade-off there, but we need to be mindful about how we are making those decisions, because there's a very high level of interdependencies that we are trying to manage. And there is often epistemic uncertainty regarding the design process that you're dealing with. Sometimes you don't really know how things are going to work out. You have a belief and expectation regarding how the future will unfold, or will you be able to design a certain kind of system in a certain kind of way. But sometimes halfway through the design process, you realize that your assumptions were a little bit faulty and you will not be able to execute them as they planned. That being said, I would like to go back to my comment regarding policymakers and the strategic objectives of these organizations regarding when they make their decisions. So when we are contracting this work, we need to be extremely mindful about how we are contracting and how we are engaging these organizations into the design process. Because during the bidding process, all of the organizations, if there's a competition, since they want to get that contract, what are they going to do? They're going to give you better estimates, even though they know that they will not, let's say, I was a part of an organization that actually did this. We thought we need 8 years to design a system. However, we really wanted that contract. So even though we knew that we wouldn't be able to design it in 5 years, we told them we could do that. And then 3 years into the process, we were like, hey guys, we need a couple more years because this is not going to work out. We knew it already. The other organization should have known it, but they let it slip and the project ended up being delayed. So we need to be mindful about these preferences of the organizations and how they can utilize their power to influence the design space and pursue their own objectives. That's a very important piece of the puzzle that I think gets often overlooked.
Thank you.
Mm-hmm.
Time for maybe one more question. Does anyone else have anything they'd like to ask?
Well, I have a question then.
Okay, sure.
What would be your definition of complexity? What would you say complexity is?
My definition of complexity. Well, I think complexity is an inherent property of systems. That's the only definition I can give you, because I refuse to give a definition that is based on number of parts or interconnections or a certain kind of shape or form or whatever, because I think understanding of complexity is also a subjective manner. So the same complex problem posed to a domain expert versus posed to an amateur who has no knowledge about it could appear less or more complex depending on how you understand those relationships and so on. So complexity is an inherent property of systems. It depends on the functions and the behaviors and the interactions and the states this system could get, but it also depends on its interactions with the environment. So for me, it is very difficult to come up with a rigorous definition of complexity. However, I can provide you with one definition, but it's not going to satisfy you. It's not going to be any better than the definitions out there. But I like the Latin definition of it. So complexity, we are acting like it's something brand new, but it's actually not. Like 2 millennia ago, Romans were dealing with complexity, and they were thinking about complexity in parts that are intertwined with one another. So it basically comes from comp, which is like parts, and lectere. Lectere is like means something like braided together. So that's how they thought of parts intertwined together, working together in such a way. That's how they defined it, which is, I think, reasonable still to this day.
Thank you.
Thank you.
I really love that definition. That's wonderful and simple. Thank you so much, Dr. Topçu, for speaking with us. This is a really wonderful lecture. We're so grateful to you for being here. And thank you everyone for also joining us today. As soon as the lecture recording is cleaned up a little bit, I'll make sure that that's goes out and is available, as well as the slides that you are graciously providing us. Again, thanks everyone. Have a wonderful afternoon.
Thank you very much for having me. And it was my pleasure to be with you today. And I hope we can meet sometime soon in person.
Absolutely.
Thanks, Dylan.
Thank you very much, Professor Mesmer. Thanks for having me.